Good morning. Welcome to the August Innovation Forum meeting. And today's speaker is from NVIDIA, which is a company that most of us are probably familiar with. What we might not know, though, is that NVIDIA also has a robotics division. So we're thrilled to be joined by Arsalan Mousavian, who is a senior robotics research scientist at NVIDIA. Arsalan's done a lot of work within the robotics and automation space, and very excited to learn more about the intersection of robotics with artificial intelligence. So without any further ado, I'll turn it over to Arsalan for his presentation.
Thanks, Norman, for the introduction. Let me share my screen. All right, you can see my screen, right? Okay. So today I'm going to talk about how to train robots in metaverse and deploy them in the real world without taking any data in the real world. So I'm going to first talk about NVIDIA and their effort in Omniverse, which is like simulation for virtual world. And then I'll go deep into some of the technical aspects of the works that we are doing at NVIDIA. So NVIDIA is pioneering AI and accelerated computing. And we work at three stages, three levels. The bottom level is basically the hardware level where we develop GPUs, CPUs, and DPUs, which in turn become integrated into very powerful servers that can be deployed in the clusters and data centers. And then on top of that, NVIDIA develops these application-specific accelerators. For example, CVCUDA is basically CUDA-accelerated algorithms for computer vision. We have like Rapids for data scientists. cuGraph is like for processing graphs, and so on. And at the top, we have these like three major platforms sitting on top of the technology stack. The first category is about NVIDIA high performance computing. So that is everything for like massively parallel jobs that require a lot of compute resources. And then there is NVIDIA AI that contains a lot of capabilities for computer vision, language understanding, speech to text. And then the final platform is NVIDIA Omniverse, which is the most relevant to the talk today. So I'm gonna talk a little bit more about NVIDIA Omniverse. So Omniverse NVIDIA has been able to develop Omniverse due to four factors. So these four boxes that you see here are basically the four pillars of Omniverse. So the first pillar is ray tracing technology, so which is called RTX. So that's basically the ability to physically simulate how the light traverses in the scene and how it bounces off of different surfaces. And as a result, it enables rendering photorealistic images that look very similar to the real images. The second pillar is the compute. So NVIDIA has been pushing the state-of-the-art on compute, on GPUs, CPUs, and DPUs. So that provides, so that will all integrate into data centers and cloud to power this virtual world. The third pillar is the USD file format. So basically, USD is originally developed by Pixar as an efficient way to represent the virtual world. So they use it a lot to create animations. But NVIDIA is also contributing to it and make it as like the main component or like the main description, main method to describe complicated scenes and movements in the virtual world. And then the fourth pillar is AI. One thing that is important is that all these amazing capabilities that you see from different models that are powered by AI models, they require a significantly large amount of training data. And collecting this training data in the real world takes a lot of time and resources. So our thesis is that we can generate these data in the simulation, and we can get annotations very cheaply and very quickly. So we build on top of basically generating this data in the simulator to train our models. So basically, all the technologies that I'm going to talk about today are all trained in simulators and Omniverse. So just a bit of more background on Omniverse. So Omniverse also has these like add-on layers on top of it that can be useful for different applications. The one that is related to robotics is called NVIDIA Isaac. So NVIDIA Isaac can be used for training agents. It can also be used for other applications. Like, for example, if you want to create a visualization to demo a customer about how their product would look like, you can use Omniverse. Different companies are using Omniverse to basically do space planning in their factories and their manufacturing plants. So you can put all these machines and all these items in the virtual factory and see how they can interact with each other and how they look like. And only after that, if you're happy with that, you can basically go ahead and build that factory. In Isaac, you can get a lot of information basically for free. So, for example, here on the top left, you can see the RGB image of the scene. You can see like the depth image, the depth image associated with that color image, and then you can also get a lot of very expensive and dense annotations quite easily. So you can see here, like on the semantic segmentation and instance segmentation, if you want to collect these annotations in real world, it basically requires you to pay a lot of human annotators to pixel each, to annotate each pixel separately, which is very time consuming and expensive. But in simulation, you can easily get this data without a lot of effort. And Isaac also provides virtual sensors for different sensors that you might have. Like, for example, it has fisheye cameras. It can simulate LiDAR point cloud. And the Isaac team basically actively developing new virtual sensors as soon as they become popular. So this list is not finalized. It can be also added through time when the new sensor or new popular technology arrives. So let's switch gear and talk a bit about the state of robotics today. So we have very capable robot platforms, like, for example, Boston Dynamics has these robots that they can jump around, they can do parkour, they can dance, but these are really choreographed for this environment that they demo these operations. So most of their focus is on control and how to mechanically design these robots to be able to do such things even in controlled environment, which is quite challenging. But it shows that the robot is already the robot hardware is already quite capable and mature. So at the bottom, and at NVIDIA, we developed this system called DexPilot that basically tracks the human hand and basically transfer the motions toward the robot. And you can see that that the robot can do a lot of very delicate tasks, which basically again is another indication that the robot hardware is already quite capable. But when it comes to deployment in the real world, most of the solutions rely heavily on smart mechanical design and also mostly blind solutions. Like, for example, they don't use a lot of cameras or any cameras at all. And basically, people design very smart, very mechanically smart end effectors for the robot to be able to do different parts of the task. And then there are a lot of fixtures and actuators that basically facilitate this task. But at the end of the day, the robot is just blindly going toward different waypoints in the 3D world. But there is a limit to basically how much smart mechanical design you can incorporate in the system. So you cannot really solve all these tasks just with mechanical design and like kind of simple perception, simple computer vision. So there are examples of it where companies went a bit maybe too much in using automation and they had to scale it back. So at NVIDIA, our team specifically works on intersection of AI and robotics to basically fill these gaps so that we can have robots do things and manipulate objects in unstructured environments with AI and also the classical methods that has been well studied in robotics. So in this talk, I'm going to talk about our approach, our general approach at NVIDIA, which we refer to it as object-centric models. So it has three main components. The first one is how we represent the scene. Oh, by the way, if anybody has any questions, feel free to ask the questions in the middle of the talk. I'm more than happy to have the talk as interactive as possible. So the first component is how we represent the scene. So the input to the system is usually the RGB or like RGB-D image of the scene, and D stands for depth. So there are these cameras that provide both color images and depth for each pixel, which means that how far that pixel is actually from the camera. So the first thing we do on these images is that we first segment the objects in the scene. So what do I mean by that? So basically, we group the pixels that belong to the same object together, and here you can see like the visualization of this object instance segmentation in the image. Then we have this mid layer, which is basically the common skills that are shared across different tasks. So here I put two examples. One is grasping, that you want the robot to pick up an arbitrary object without training on that object before. So you want to have this general capability for the robot to be able to pick up any object. And the second one, this is again an example that you want to basically plan motions that are where the robot goes from point A to point B. without colliding anything in the environment. And the highest level of the stack is these policies that are basically accomplishing the task, but they use these common skills as their actions, and their job is to come up with a series of the actions that accomplish the task. I'm going to talk about these two examples of the policies that you see here. So does it make sense? Is there any questions so far?
Arsalan, really quick, from your point of view, from NVIDIA's point of view, what do they hope to get? What do they see as the business case for all of this? Out of curiosity, I think you mentioned that in our last video.
Yes. So basically, if I go back here, so what NVIDIA is looking for is that we want to provide the brains for the robots, so that when people want to deploy the robot, they just buy NVIDIA hardware with the software that makes the robot valuable to the customer. So basically, we want to lower the barrier to entry for adopting new robots by providing both suitable hardware and the software. So we are working on the software side of things, and NVIDIA has this line of product called Jetson. So they have these different chips that are designed for embedded systems, and basically that is the hardware effort of NVIDIA for the embedded systems. And the Jetson chips are already deployed in a lot of autonomous cars, autonomous vehicles, and also car manufacturers like Mercedes. They use that to provide these driving assist features, like, for example, to detect like lanes, cars for the car. So they are all powered by Jetson.
I just really quickly, I think when your NVIDIA's solutions hit the industrial marketplace, it'll feel a little bit to us like plug and play, won't it? It'll be like,
yes,
yeah. I think this is an amazing future to look forward to.
Yeah, definitely.
Thank you. Thanks for the sidetrack.
Yeah, no problem. All right, so let's talk about so today I'm going to talk about first grasping, like to showcase some of our works on grasping, and then I'll talk about object instance segmentation. In the interest of time, I'll talk about the two policies that we have for image conditioned object rearrangement and language conditioned object rearrangement. So first, I'm going to talk about how to grasp unknown objects. So the input to the system, as I mentioned before, is the RGB-D image of the scene. And we basically take the depth information and project it back to 3D, and to basically get the object point cloud, to get the point cloud for that object. And the goal in grasping is to predict the goal poses for the robot, so that if the robot goes to those positions, if the end effector and gripper goes to those positions and close the gripper, they are able to pick up that object. So here, at the very high level, we basically have two models that are trained in simulator. The first one proposes these different grasp poses. One basically evaluates these proposals and see how likely they are to succeed in grasping these objects. And we train everything in simulator. So in order to train this system, we basically simulated 17.7 million grasps in the simulator. So you can see on the top right that for like a single mark, we sample different grasps. We basically shake the object to basically see which grasps are stable and gonna be successful. And we did this experiment. We collected this data set on a lot of meshes. So we collected 8,800 meshes from 262 categories. And imagine that you want to collect equivalent of this data in the real world with the robots or even with your hands. How long it takes to do 17.7 million grasps. So it takes a long time. But it turns out that with the technology that we develop in-house at NVIDIA, with the physics engines that allow for parallel simulation of contact-rich interactions, we can speed this up and collect this data in just 2 days on 16 GPUs. So basically, instead of trying out things in the real world, we can basically use the compute to massively do these experiments, like basically brute force it in the simulator to collect this amount of data in a short amount of time. And then we use it to train this system. And it turns out that if the quality of the simulation is high enough, you can basically train in simulation and deploy the system in the real world. So we never trained these models on these objects, but they are able to work in the real world without any adjustment. So basically, whatever that is trained in simulator, it can be deployed in the real world.
So Arsalan, this is Kirk again with another question. This everything you talked about with robustness and generalization, because that's what we kind of do as humans, is we just generally get the idea of a doorknob, and now we can open all the different types of doorknobs. And these simulations happening so quickly, and I'm seeing this array of different things that weren't even trained on. What happens with mistakes, though? So I'm sure in your testing, if the robot did make some mistakes, do you have to go back to your simulation, or how does the feedback loop go?
That's an excellent question. So the first way to handle the failures is that these systems, like as I showed here, they don't just have one single solution. So they propose a lot of different solutions. So for example, if it fails on the first attempt, you can run inference again and choose another sample and execute that one. And basically, if you can do like multiple attempts, that already improve the success rate. But there is this other pillar as well, that we often we make the training scenarios more complicated and more challenging, to even more challenging than the real world, to make the systems more robust, so that the need for reattempting goes down. So as a result, you gain more robustness, basically. And the third way that is possible, but we haven't done it quite significantly so far, and the reason is that we want to basically develop a system that can produce value from day one. But you can always feed back the failure cases in the real world and fine-tune your models using the real world. But we are doing our best to minimize the need for such a fine-tuning in the real world, so that we have this like frictionless deployment in the real world. Does that answer your question?
Yes, and I'm stunned at, because I was thinking of I'm just using tennis as an example, but a tennis player at the high school level, and then a tennis player at the college level, and then at the pro level, and maybe the Olympic level, there are certain skills that they develop at those different stages. But it seems like you're able to program in through the simulation so many levels of excellence or advanced capabilities, like you said. So the system will add value from day one, but also minimize that need for that refinement. I had no idea that this was even being worked on. Anyway, mind blowing.
Yeah, this is basically the common theme throughout the talk. So we are using simulator in everything, in all the projects that we are working on.
And Arsalan, if I could jump in as well, and this is truly fascinating, very exciting frontier. I know when we last spoke, we talked a lot about grasp post detection and how important that is.
Yes.
Are your simulations modeling through these millions and millions of grasps to identify the best poses for objects and then to replicate that within the real world? Can you talk a bit more about your work within grasp post detection and how there's applications within manufacturing for that?
Oh yeah, definitely. So basically what we do in simulation we have this like repository of 8800 meshes from a lot of different categories. And then for each object, we try them out in the simulator to find out a set of successful grasps and failure grasps. And by the way, failure grasps are also equally important, because unless you know how to fail in grasping something, you cannot make it better. So the model takes advantages of both successful grasps and the failure grasps. And then we create a lot of virtual environments by putting these objects in the scene and we already know these grasps. So if you look at these green lines at the lower bottom around each object, so these are basically the grasps that succeed in on each of these objects. And basically we train this model on a lot of different categories, and we want the model to be able to come up with the to be as close as possible to the ground truth. And through this process, the model learns to extract the common things that generalize across this large scale training. So what would happen if we just train on a very small set of categories? The thing that would happen is that the model would overfit to that specific category. But when you scale up these trainings, it can actually learn useful properties so that it can generalize to even objects that are outside of the categories it is trained on. Because like it kind of learns like if I want to put it in simple words, it kind of learns the common sense for grasping, like what kind of geometries are useful for grasping, for a grasp to succeed. Does that answer your question? Oh, and then just for the second part, like in manufacturing and also in warehouses, a big portion of the problem, like the ability that keeps coming up, is that you have this like set of objects that you want to empty out like a bin, or you want to put an object into a machine for machine tending. So all of that requires robot to be able to pick up different objects, and basically so that's why we focused on grasping objects in the beginning.
Great, thank you, Arsalan.
Yeah. And we also extended this work to robot object handover. So here we basically track human hand and also segment the object that is in hand, and we generate the model on the fly proposes a set of grasps, and then we plan a motion that avoids human hand and reaches to one of these grasps to be able to pick up that object. And we also extended this to cluttered environments, because so far the works that I've talked about, they were tailored for single object pickup, but any object. But in real world, we have like the robot needs to deal with clutter as well. So it needs to avoid hitting other objects and be able to grasp these objects. So I won't go through technical details, but at the high level, it is still uses the data from the simulation to basically generate these graphs. And you can and this is basically the deployment in the real world. So for example, we never trained this model on the objects stacked on top of each other. We basically created like random scenes, random clutter from the data set that I talked about earlier. And here you can see like how it performs in the real world. So from time to time, like for example, for that plastic mustard bottle, you saw like the failure, but like it keeps going forward, like for different objects. And yeah, so this is the grasping work that we have. And then we also benchmarked it in the real world, so it achieves like 91% success rate without any fine-tuning or changes using the real data. But we tested it on kind of adversarial setups. So usually in different projects, we rarely see failures of these of the grasping, and most of the time, if there is failure, we can do re-grasping and re-attempting that object, and it usually succeeds. So then the next part that I'm going to talk about is object instance segmentation. So as I mentioned before, in object instance segmentation, we want to group the pixels that belong to the same object together. So on the right, you can see like an example of object instance segmentation, but we want to also be able to go beyond just single image. We want to be able to track objects through the video, which is called object tracking. And we want to also be able to detect objects by just providing few examples of that object without retraining on that object. For example, let's say you have a cabinet full of different mugs, but you want your robot to bring your favorite to take out your favorite mug from the cabinet. So you are not looking for any mug. You are looking for a specific mug. So that problem is called few shot detection, which basically means that you are not training on these novel categories or novel instances. You just want to provide few instances of that object, and you want the model to be able to detect it. So I'm going to give a high-level idea behind this behind this technology. So we basically do three things. The first one is object detection. So that is the problem of finding the object, finding any object in the scene, and basically extract a bounding box around that object. So that is called bounding box object detection, which is basically finding a bounding box around each object. After that, we label each pixel within that bounding box to see whether that belongs to that object or not. So on the top right, you can see the segmentation for each object. But with these two, you can just say that which pixels belong to which objects. You cannot really identify these objects for tracking or for few shot detection. So what we do is that we learn this signature for each object, which is a very high dimensional vector, continuous vector that is basically a fingerprint. You can look at it as a fingerprint or signature of each object. And when we want to track the objects through the video, at each frame, we detect these objects, we compare the signatures of these objects, and we associate the objects with similar signatures to each other. And we train this in simulation. So here you can see the images that we can produce in simulation. As you can see, they look very close to the real images. And on the next to each of these real images, you can also see the ground truth annotations that we get for each object for free. And we created 350K scenes and rendered them. And that, like this data generation process also takes like 1 or 2 days. So this is also like another example of how you can use the compute to create the training data that is not easily accessible and possible to do in the real world. So in the virtual world, you can do all of that and train your models and basically deploy them in the real world. So we integrated this technology into our system. So now let's say you want to pick up a certain object that is like, for example, designated by the query view on the top left of the image that is taken. So that is the image of the object taken in another environment. And you can see that the model is able to detect that object both in the external camera and also on the wrist camera. And then we use like the grasping works that I talked about to basically generate grasp. We also have other works that I haven't talked about today about creating collision-free motion so that the robot can reach to those detected grasp poses and avoiding obstacles. So here you can see like the combination of this technology in the real world on a real robot. And we basically tried it in different parts of the kitchen to showcase the generalization. Oh, and the fun fact is that we never trained on actual kitchen. So we trained on like maybe different environment, like tabletop scenes, like just a table with a bunch of objects, and some shelves that we procedurally generated, like as opposed to trying to make a replica of this kitchen, we just randomly create like different shelves to create this environment. If there is any questions so far, I'm happy to answer. All right.
Hey,
So
I had a quick question.
go ahead.
So when you look at deployment and maintenance of these manufacturing, commercial spaces, what types of workforce skills do you see needing to both support the equipment and also interact in just from an operations perspective?
Yeah, that's an excellent question that it will be clear more in the last part of the talk. But you pointed out a very important issue right now. So right now, most of the robotics group and in all these different companies, they kind of make systems that require some prior knowledge or some expertise to be able to even run these systems. But when you want to deploy them in factories and manufacturing plants, as you were kind of pointing to, you need to make the system in such a way that anybody can interact with these systems without requiring to go to grad school and like work with robots and like be familiar with all these technologies in AI domain. So far, I just talked about like the technology side of it, like how we develop these systems. But in the last part of the talk, I'm gonna showcase some works that are basically trying to abstract away the complexity behind and make them usable without requiring a lot of prior knowledge in robotics.
Thanks.
So that brings me to image-based object rearrangement. So so far I just talked about like different capabilities that we developed for the robots and how they can fit together. But how we can make this process even simpler. Like for example, let's say I want the robot to move these objects around in a particular way. Instead of programming the robot to go to different coordinates, one way that we can specify the goal configurations is to just provide the target image that we want the robot to achieve. So for example, you can see that in future we can have solutions that if you want your robot to do a certain task, you just take it for you just create that target configuration that you want the robot to achieve. You take a snapshot of that, and you want the robot to basically achieve that. So that basically removes the need for any expertise in robotics. So it's basically gonna be as simple as just doing it yourself once and taking a snapshot, and then the system will take care of the rest. So that is what is called image-based object rearrangement. So the image-based part is from the part that you want to provide the target image, and object rearrangement is basically this family of works and a line of research in robotics research that focuses on how to rearrange objects for different tasks. And if you think about it, most of the tasks are basically object rearrangement. So for example, you can basically use this image-based object rearrangement in repetitive tasks where the goal can be represented by just a single image. So for example, if you want, let's say you want your home robot to set the table, you just and you want the dining table to be exactly in the same arrangement every day, you just do it once and then the robot will take care of it. Or if you want to organize items in the cabinet, or in the industrial settings, if you want to do packaging, for example, where each object needs to go to certain areas, so you can show the image of the ideal arrangement that you want to achieve, and the robot is able, and this technology is able to come up with a series of action that achieve these target goals. So I'm gonna give like a high-level idea about this technology, and this is, by the way, a very active area of research in our team, and we are working on improving it constantly because we believe this issue of requiring expertise to operate robot technology in the world is one of the biggest barriers in mass adoption of robotics. So we start with the goal scene that is provided to us, and at the top you can see what the robot is observing in the beginning. We use our object instance segmentation to segment these objects, and we also train another model that basically for each pixel predicts the displacements of each pixel. So for example, for the orange juice, it predicts for each pixel how much, what is the delta x, delta y in the pixel coordinate to go from the current image to the goal image. And then we use that to compute the motion that is needed for each object. So in the flow minimization block, you can see those arrows that are that are showing the transformation needed to go from the current image to the target image. And then we choose, and then the planner basically chooses the object that is farthest from its goal location, and that's how we select the object and use the grasping capabilities that I talked about before, and also some other technologies to pick this object and place it at that final location. And this model is again trained in simulator. So we created a lot of different object rearrangements in the scene in the virtual world, and then we compute the pixel displacements for each pixel, and that would be used as a signal for training these models, so that in any scene, given any pair of images, we can find these displacements and compute the transformations. And another example for basically making an intuitive interface is to communicate with the robot through language. This is also a very hot new area that is very active, and as you know, it is like fueled by the great successes that large language models such as GPT models and ChatGPT have. So the task is the following: that we observe the scene, and the goal is to basically, the goal is given as a sentence. So the sentence here is like sort fruits on plate and bottles in box, and the robot automatically breaks down these high-level command to some sub actions, and basically we use our technology to accomplish these subtasks. And as you can see here, for example, it knows that the bottle is not a bottle, so it won't even touch it. So and we never say that, okay, pick up the banana. We just say sort fruits on plate, and the model itself figures out what are the sub goals that are needed to achieve. So in this work, we actually didn't train any new model. So this is built on top of large language models. So what we do is that we provide our set of functions as a prompt to GPT-3 model. So these models are trained on a lot of, in addition to a lot of text on the internet, they are also trained on a lot of codes, like in Python, C++, like programming languages. On GitHub, like people put a lot of codes on GitHub, so they trained on those as well. So these models have like both ChatGPT and GPT-3, which was the predecessor of ChatGPT. They have very good understanding of programming languages and also semantic understanding of the word. So if you design your prompts carefully, they are able to extract knowledge from that prompt and be able to generalize to new tasks. So here is an example prompt, and I'm going to talk about what the details of what you see here. So basically, we kind of came up with a syntax that is close to Python language, so the import statement in Python language is basically for defining the functions that you want to use in your code. So here, the functions that we define are the functions that we created ourselves using the technology that we have. So for example, a function that you see here is grab and put in. So that takes 2 arguments, and it grabs the first object and puts it into the second one. So for example, it can be grab and put in. The first argument could be the bottle, and the second argument could be the box. So that means that we want the robot to pick up the bottle and place it in the box. And then we show few examples of these tasks. Like for example, we basically say that okay, if the goal is to throw away the bananas and the objects that you see are banana, garbage can, and like bunch of other objects, the solution to this problem should be just grab and put in banana and garbage can. And then we provide like few other examples. And then at the test time, when the user asks about, okay, that I want to sort fruits on plate and bottles in box, we convert that to a Python function, and we also detect all the objects in the word, all the objects in the scene. So we say that, okay, we see a banana, we see a bottle, we see a box, plate, table, drill, and a strawberry. And this LLM, the GPT-3, without any training, like basically the model that is trained on internet, on large scale data that was collected on internet, is able to break down these tasks to these individual steps. And we already have implementation behind these individual steps, and we know how to execute them. So basically the large language model breaks down these problems for us and sequence these actions so that we achieve these tasks. So a lot of different teams in all the big tech companies are doing a lot of cool research in this area, which basically combines the advances in large language models, computer vision, and robotics together to provide more common sense and a more intuitive way to interact with the robots. And yeah, that's it. So if there are more questions, we can go over them, we can discuss more. But one thing that I wanted to point out is that in research, half of the success is coming from asking the right question. And it is really important for us to know the use cases and maybe like the pain points that you have with using prior robots technology so that we can guide our research to address your issues and your concerns as well, and make it also more useful, because at the end of the day, we want to release this technology to manufacturers, to factories, so that they can use automation and robotics in a more intuitive and cheaper way.
Well, Arsalan, thank you so much for that presentation. Along the lines of use cases in manufacturing, so as this technology becomes more prevalent with a variety of use cases commercially, based on your understanding of this technology and where you see it going, what advice would you give to small and mid-sized manufacturers and folks on the call on actions they can take now and in the near future so they can be well postured to adopt this technology?
I think there are two ways. There are two things that needs to happen at the same time. So one way is that in the technology world, we need to know what the problems are. So there needs to be some way of advertising the problems that manufacturers care about. So that's one part of the equation. And the second part is that all these technology companies, including NVIDIA, they have these big tech conferences that they showcase the latest and greatest of their technology. And in those conferences, you can connect to these companies to see how they can partner or how they can use these technologies. And I said two ways, but there is like a third way as well, and that is like in automation trade shows, there are always these companies that are showcasing their products, and basically the main reason for those trade shows is to connect technology companies to manufacturers and automotive partners to basically first showcase it to them, and also teach them how to use that technology and deploy them for manufacturing.
Wonderful. We have just a few minutes remaining. Are there any other questions from the audience?
Arsalan, I just wanted to mention, in case somebody is working on another question here, it's amazing that you walked us through the all of the steps of development and I'm thinking about all of the problems that you've solved up to this point, even to the point of programming the robot with language. So I'm just curious about how long has it taken to get to this point? How long have you seen this in development?
So I've joined NVIDIA in 2018. So it's been almost 5 years. I think a week from now, it's going to be exactly 5 years that I've been at NVIDIA.
Congratulations.
Thank you. And then the works that I've talked about today are from these like past 5 years. So our team started 6 years ago. In general, like before that, there wasn't any robotics research team at NVIDIA. But I've been part of these efforts for the past 5 years. And this is like just a subset of the works that we are doing at NVIDIA, because I didn't want to bombard you with a lot of different works. So I wanted to have like a flow of subset of works that go together well and will tell a coherent story, because we are working we are a big team, so we are working in a lot of different directions.
I see. Now, you mentioned that some of your technology was developed by Pixar.
Yeah.
That was really interesting. Are you seeing other companies that are innovative that are, I don't know, that you guys are keeping an eye on and saying they're developing something we might be able to integrate or use? ChatGPT was another example.
Yeah. So let me just go to this slide. Yeah, NVIDIA is partnering with a lot of external companies. Like, for example, in robotics, we are working with robot OEMs, like all the major ones, like Fanuc, KUKA, URs, Universal Robots. So a lot of them also approach NVIDIA because they know that because they are aware of the efforts that we are doing at NVIDIA. We are also working with Microsoft and Amazon on the cloud as well. So NVIDIA is partnering with actually quite a bit of other external companies on different efforts.
Wow, man. I think that should give all of us hope, for the good things that are coming our way. This has been an excellent presentation.
Yeah, thank you.
Yes, thank you so much, Arsalan, again, for joining us today and sharing your insights, giving us a peek behind the NVIDIA curtain, if you will. I found it very fascinating. I'm sure the folks on the call did as well. So we are just about out of time. So thank you, everyone, for taking time out of your busy schedules to join us today. Our next meeting will be Wednesday, September 6th, and we are finalizing those details, and we'll get that announcement out soon. So with that, have a great day, everyone. Take care.